So welcome back to chemistry online class students. Students, yesterday at the lecture 12, I completed very importantly VSEPR theory, that is predicting shapes of the molecules depending upon number of electron pairs, bonding pair of electrons and lone pair of electrons. Okay. And now today just will continue very important another concept called as resonance. This resonance concept will help you for both organic chemistry as well as inorganic chemistry. Let us understand in detail. Okay, so be very patient and listen the lecture carefully. Okay, right. First of all, the question arises: what is resonance? The resonance, means students, it is resonance is the shifting of pi electrons or sigma electrons from one position to another position. In a covalent molecule. Or lone pair of electrons. From one position to another position in the covalent molecule to become stable. Okay, that means resonance involves delocalization. Delocalization, that's only shifting the pi electrons or lone pair of electrons. Remember, not sigma electrons. Sigma electrons are not involved here. Only pi electrons or lone pair of electrons from one position to another position. Why? In order to become stable. That is called resonance. Then, by undergoing resonance from one position to another position, next they will use a structure called as what? Resonance structures. What are these resonance structures? But before we get to resonance structure, for resonance structure, one condition is compulsory. Conjugation is the necessary condition for resonance. Very important. Resonance. Conjugation is a necessary condition for resonance. Conjugation means a compound should contain alternate single and double bond. Compulsory alternate single and double bond. That is called conjugation. Then what are the resonance structures? Resonance structures or also called as canonical structures. Okay, are the structures with same nuclei, okay, same bonding and non-bonding electrons, same nuclei, same bonding and non-bonding electrons. I1 that means canonical structures are the structures which are having same nuclei, same bonding electrons and non-bonding electrons, which gives the adequate information about the molecule. Because see, why you have to study resonance structures and the resonance concept? Because Lewis dot structure you studied. Lewis dot structure is inadequate to explain the structure of atom, or structure of molecule. Inadequate. It is giving incomplete information about structure of a covalent molecule. So, in order to get the adequate information about the molecule, about its stability, this concept has been introduced by the scientist Pauling. Okay, resonance was this concept was introduced by Pauling. Accordingly, what is resonance? It is the shifting or delocalization, or movement of pi or lone pair of electron from one position to another position in a covalent molecule to become stable. And for the resonance compulsory, the covalent molecule, the compound should contain alternate single and double bond, whether inorganic or organic. Both it is important. And whatever resultant structures, they are called resonance structures or canonical structures or canonical bonds. Then what are these? These are the structure of molecule with same number of nuclei, same number of bonding and non-bonding electron, which gives us the complete idea, complete information, that is adequate information about the structure of the molecule in terms of what? In terms of structures. That I will explain you with the example. Okay. But out of these resonance structure, but very important point, but resonance hybrid is most stable. Complete adequate information about the structure of molecule. But resonance is the most stable structure of resonance structures. Okay, resonance hybrid. And question arises, so what is this resonance hybrid? Resonance hybrid is just nothing but resonance hybrid is the most stable structure of atom, structure of molecule, which gives properties of molecule, which gives all properties of molecules in a single structure. That means in terms of nuclei, in terms of that is bonding and non-bonding electron. It is the most stable structure of molecule, which gives all information about the molecule or all the properties of molecule in a single structure. There is no need to depend on other first, second and remaining, that is what? Preceding resonance structures. Got it? So this is about a very important point to be noted before going to write the resonance structure. And repeat, what is the resonance concept, students? It was given by Pauling in order to explain, in order to get complete information about structure of organic molecule, which is inadequate information as given by Lewis dot structures or Lewis dot formulae. So what is resonance? Resonance involves delocalization or shifting of pi electrons or lone pair of electrons, not sigma electrons, from one position to another position in a covalent molecule, that too containing conjugation. Conjugation means alternate single and double bond. That's why conjugation is necessary condition for resonance. What is the aim? To become stable. The resulting structures are called resonance structures. What are resonance structures? Resonance structures are also called canonical structures. Canonical structures are the structures which are same with respect to nuclei, same bonding and non-bonding electron, which gives adequate information about the structure of molecule. But out of them, the resonance hybrid, last one, is the most stable structure of resonance structures. But what is the resonance hybrid? It is also the most stable structure of molecule, which gives all the properties, all the characteristics as a whole for a molecule. Therefore, resonance is characterizes bond characters, or as a total, it is a characteristics of the all the properties, characterize the bond properties in a molecule. Got it? Now next question arises, what is resonance energy? After understanding all this, what is resonance energy? Resonance energy. Resonance energy. See here students, resonance energy is nothing but resonance energy is the difference in energy between the resonance hybrid and most stable canonical structure. So that is called resonance energy. Lower the resonance energy, higher the stability. Higher the resonance energy, lower the stability. So best example is, we start with the structure, that is benzene. Benzene is having lowest resonance energy of 150 kilojoules per mole. Okay. Right. Now see, these all points you come to know by writing the examples. Otherwise you won't understand. That's why we are starting with the example. Best example, especially this resonance concept, it help you very much in aromatic hydrocarbons. They contain a compulsorily alternate single and double bond. Apart from that, conjugated dienes. Conjugated diene means compounds containing alternate single and double bonds. Okay, and especially multiple bonds also, that means triple bond compound also, it is same. Let us see with the example. Best classical example to convince you is resonance and resonance structures, resonance hybrid and resonance energy. The best classical example is benzene. Benzene is having formula 6H6. When it is done structurally, this is a structural formula of benzene. See, benzene is containing 6 carbon, 6 hydrogen. Okay, but see here, single bond, double bond, single bond, double bond, single bond, double bond. This is called conjugation. Now it will exist. How? Bonds it will shift. And remember, this resonance is indicated by double-headed aroma, not single-headed. Double-headed aroma means resonance structures are interconvertible, they are reversible. See here. Now this will shift over here. As a result, this will shift, and as a result, this will shift. This is called. See, that means I told you in double bond there is one sigma and one pi. See, this is delocalization of only pi, not the sigma, or else lone. Got it? Therefore, see here, the second resonance structure for benzene is. See, now they are shifted here. As a result, this bond will go here. As a result, this bond will come here. This is first. This is second. Therefore, see, resonance hybrid is this. Resonance hybrid is this. See, we have started down from here, right? And ended here. That's why this is called resonance hybrid. Resonance hybrid. Resonance hybrid, what it tells? Double bond has started elongation from here and ended here. That's what saying. Okay, and see, this can also be just written as generally length. One full atom. This is electron cloud. This is pi electron cloud. What it shows? Electrons, pi electrons in benzene are not in static position. They are always in movement. Start delocalization from here, ends here. Once again start and ends back. That's for interconvertible. This is called resonance. Okay? That this is one example again. Like this will go for next 3-4 examples will come to know very easily. Right. This is the first example. And remember it has resonance energy of benzene is very less. It is about 150 kilojoules per mole. 150 kilojoules per mole is the resonance energy of that is benzene. That means the most stable canonical structure is second, and this is resonance hybrid. The resonance hybrid minus the most stable canonical structure. This will give you experimentally resonance energy. How, sir? By X-ray diffraction method or by spectroscopic method, they will give the information of the bond length, and that will calculate in terms of bond energy. It is only 150. So lower the resonance energy, higher the stability. Got it? This is one example. Now students, let us go to another best example to convince you this resonance by reorganization of pi electrons. How it helps in organic chemistry and even in conjugated ions. Best example I will give you carbonate CO3 2 minus. Okay. Lewis dot formula for carbonate is C double bond O 2468 2468 2468. And this is first. Okay, this is carbonate. What unit? 2 minus. Now delocalization, you see, these are called lone pair of electron and one pi electron. Only disturbing pi and lone pair, not sigma. Remember. So now this pi electron will shift here as a result. This will come from here. Okay? And you just observe how it changes. Second resonance structure for carbonate radical is single bond O 2 4 6, right? Positive, and here as well 2 4 6, and here it's a bond because see 2 4. These electrons shifted, lone pair shifted to form pi electron. This is second resonance structure. Second resonance structure. Got it? Very simple. Now what is third? As usual. This will shift over here. Is lone pair. I will read back to counterbalance the tetravalency. See here. What will happen? Valence tetravalency of carbon 1, 2, 3, 4. Right? If this electron shift here, double bond, valence will become 5. In order to restore it tetravalency, this will shift here. देखो को प्ले जैसा करना है क्या है ये इलेक्ट्रॉन्स क्या हो गया डीलोकलाइज बॉन्ड कैरेक्टर में हो गया दो इलेक्ट्रॉन्स माने तो एक बॉन्ड हो गया एज वेल कितना हो गया 1 2 3 4 5 हो गया 5 है क्या कार्बन का नहीं इसलिए क्या करना है इसको रीस्टोर करने के लिए इसको शिफ्ट करना है तो ऑटोमेटिकली हो जाएगा देखो इधर एनी डिस्ट्रीब्यूशन ऑक्टेट नो 2 4 6 8 2 4 और ऑक्टेट राइट लाइक दिस हियर आल्सो चेक दिस विल शिफ्ट हियर एज अ रिजल्ट 1 2 3 4 to restore it, it will shift. So the third resonance structure is what? See, O, right, positive, negative, and here double bond, right, and here 2, 4, and it's a single bond, 2, 4, 6, over and after. Okay, this is how we can write CO3 to 1. This is third resonance structure. See what we are coming here. See what coming. I told you resonance structure are the structures. These are called resonance structure. There are 3 resonance structures for carbonate radical. Radical it is not a ion. It is negatively charged divalent ion. Okay. See here. Same number of nuclei, same number of bonding and non-bonding electron, bonding and non-bonding electron, even restoring octet, no disturbance in the octet. Got it? Now you see, double bonded started here, to shifted here, once again to shifted here. That is can be shown in resonance hybrid methods. See, let us see. 1, right? 1, 2 and 3. So this is shown by this. 1, 2, 3. Double bond we have started here, right? And we have shifted here, and we have stopped. This is called double bonded here, and this is called resonance hybrid. This is resonance hybrid. The most stable one is resonance hybrid, not the resonance structures. Got it? The most stable structure you can give the information of all the molecule in a single structure. See, here one pair of electrons not written, one is not written, it's okay. But see, 2, 4, 6, 8, 2 lone pairs, here also 2 lone pairs, and here also 2 lone pairs. And this double bonded character compulsory have to show like this, only the dotted line. Okay. This is called resonance hybrid. Resonance hybrid. Got it? I think now you are getting it. See, let us for your purpose just I'm writing, not necessarily to write numbers in T. Right, that's about the resonance structure of carbonate radical. Generally for 3V, they may ask you for 2 marks, but not ask you, but remember. Now once again, resonance hybrid, this minus this will give you resonance hybrid. That's it. After carbonate radical, let us will go for same another example. Same manner I will show you nitrate radical. Let us start with another example, nitrate radical. The same manner. Now you have to know very clearly. Practice it, definitely you will enjoy it. Otherwise, very difficult. Okay. In the same manner, NO3 minus nitrate radical. I will show you. Nitrate, N double bond O and O. Here also 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Got it? This is nitrate. Okay, NO3, what it is? Minus NO3 minus. Now once again you see here, students. This will shift here. This will go back. And this one forms N double bond O, single bond O, 2, 4, and this is 2, 4, 6. The single bond 2, 4, 6. Positive. This is negative. Less electronegative atom positive, more electronegative atom negative. That's it. This is second resonance structure. Second resonance structure of what? Nitrate radical. Now add one. Once again, this will return here as and this will return back. Okay, then what you get? Once again, shifting here, double bond, here, single bond, 2, 4, 6, 2, 4, 6, 8, and this is as 1, 2, 4, 6, 8. Okay, this is third resonance structure. Very simple. Very simple. Just what I am playing game here, shifting of that is pi electrons and lone pair of electrons. And most stable resonance hybrid. Once again, I will 1, 2, 3. 1, 2, 3. We have started double bond here. We have shifted here, and we have ended here. Got it? Same. No change. No change. No change. No change. That this is nitrate radical. Resonance hybrid resonance. Alright students, therefore see all the three, 1, 2, 1, 2, 3, 1, 2, 3, shifting of what pi lone pair double bond is characterized in a single molecule. That's what is called resonance hybrid. What I told you, it is the most stable structure of molecule which can give the properties of all the molecule in a single structure. So that is the most stable. The difference in energy between the most canonical, that is third, minus this resonance hybrid is resonance energy. That's it. This is about nitrate. See now that we have learned three examples, right? Best classical example, benzene, then carbonate, then nitrate. Got it? Okay. Now students, let us come to another one example. Very interestingly, carbonate, nitrate, benzene, which has overall. Another example, ozone, which is for your theory syllabus, which is very, very important. Let that important. Just see. Ozone, you know, double bond, single lone pair of electron, single bond, three lone pair of electron. This is first one. So give only two resonance structures. What will happen? This will have to shift here. As a result, right? And this will over and down. Any one, either, but only pi, not sigma. Remember, this is not disturbed. Single bond. Okay, 2, 4, 6, and here double bond. Right? 2 and 4. See whether any disturbance in lone pair of electrons or any that is restoration in the octet. No. See 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Here also only what shifted this bond from here to here. That's it. That is called resonance. And that's why resonance hybrid is what? Resonance hybrid is very simple, very simple. And this side also. This is resonance hybrid. Like this, you can learn so many examples for resonance structures. Very good example, important for theory purpose for 2 marks. Okay? Right. Now, afterwards, this resonance structure of ozone, carbonate, nitrate, benzene, some more examples they give you, especially for CET purpose. This is CO2, carbon dioxide. C double bond O, double bond O. Okay, 2, 4, 6, 8, 2, 4, 6, 8. Now this is completely stable. This is 1. But see here, these electrons sit here as a result. This will delocalize, giving carbon, sorry, oxygen 2, 4, 6, 8, negative, positive, single bond, okay. And here, triple bond will come, and this is positive, right? See, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now once again, as early as possible, almost all. Now the single bond will come on. That means these bonds will shift over. As a result, these bonds will shift, giving rise to it. This is somewhat tricky. Triple bond, single, okay, and this is 2, 4, 6. This is another resonance. This is a linear bond. Okay? So this is negative. And this will be, sorry, neutral bond. This will be. Like this will shift from one position to another position. Okay? This is third resonance. That's what resonance hybrid for this one again, right? Already is written only. Double bond, over and down. This is resonance hybrid. Okay, this is linear molecule carbon dioxide sp hybridization. Okay, right. So that's about shifting of from one position to another position, restoring octet, not disturbing in the nuclei when bonding or non-bonding electron, so as to become stable. That's it. That means by undergoing delocalization, they lose energy and become stable. That's it. Very easy. This is for carbon dioxide. In the same way, the most stable resonance structure for carbon monoxide is very important. That is carbon monoxide. Generally, carbon having 4 tetravalency and oxygen 6. 2, 4, 6. Carbon only 2, 4. Will form first double bond according to Lewis dot formula, right? This is one. But most canonical stable one is this will shift here as a result. Carbon triple bond. Okay, positive, and this is that's it. This is the most stable resonance hybrid for the carbon monoxide. See, here it is 2, 4, 6. Carbon was 6, but the oxygen octet. The most stable structure for carbon is this one. 2, 4, 6 and 2, 4, 6. And both are octet to each other. This one the most stable Lewis dot formula for carbon monoxide. That's it. So that's about resonance hybrid what we can write here. See, okay, double bond O and this is resonance hybrid. Not necessarily this is more than enough, right? That's about resonance. Consult and delocalization. What is the resonance? It is the experiment of displacement of pi or lone pair of electron from one position to another position in a covalent molecule so as to become stable. And this is observed only when compounds they contain alternate single and double bond. That is called conjugation. And structures are called resonance structures or canonical structures or canonical forms. That means they will shift in terms of what? Lone pair as well as pi electron, not single, not sigma electrons. But they will not disturb the octet. They will restore octet and become stable by losing energy. That's why resonance hybrid is the most stable canonical structure. Most stable structure of all these canonical structure, which will give you complete information about molecule in only one single structure. That's why, as a whole, resonance hybrid characterizes the molecule. Bond characterizes whole as a molecule. Okay, right. But very interestingly, see, after understanding all these examples, very funny. These all are written on resonance structure. They are only theoretical. They are hypothetical. Nothing is prepared in the laboratory. Lastly, very interesting thing. Resonance structures are hypothetical. Hypothetical means man-made conventions. Uhe madittu. Hypothetically means man-made conventions. No, nothing is. That means no any structures exist actually. Nothing is prepared in the laboratory. In the laboratory we cannot prepare these resonance structures. In the laboratory we cannot prepare these resonance structures. Only they are hypothetical. Theoretically they are hypothetical. They are stable, but practically they are not prepared in the lab. It's a very strange thing. Okay, right. So that's about concept of resonance. Right, students? So now I will stop here. Okay, students, see after understanding resonance structures, resonance hybrid, resonance energy, right? Once again I will if it is yesterday's VSCPR, last lecture's VSCPR table, which is very important, see, which is helpful for your CET purpose. Suppose the type AB, there are 2 lone pair of electron, all bonding pair, no lone pair, hybridization SP, okay, geometry example, no deviated geometry. If a whole pair of electrons are zeros, will not affect the geometry. If for examples are barium chloride, okay. Even you can also give another example. Best example is barium chloride. Be is near to. Okay, even BeF also I can give. But next one, this is the completion of first one. All are bonding, no change, no lone pair. If lone pair enters, see, A, B, total. Two bonding pair, one lone. Hybridization. So total 2 plus 1, 3, right? That is sp2 hybridization. Real actual, it is triangular planar. But deviated geometry is bent. Example, O3 and SO. O3 and SO. Just see like this. O3 and SO2. Got it? Okay. Next. This is a two bonding pair. One load setting vector. Triangular planar to bend. This is deviated geometry. The same example, if over and out, if there is AB3 molecule, 3 bonding pair, 1 lone pair, right? Total 4, sp3. It should be tetrahedral, but no, it's a trigonal. Deviated is what? Trigonal pyramidal structure. An example, it's the best example, ammonia, NH3. Right? Ammonia, pyramidal structure. Due to one lone pair instead of tetrahedral, it is seen. Like this. 1, 2, 3. With all hydrogen, and 1. Pyramidal structure. Right? Deviated. No, sir. Here itself, if it is same AB type, 2 bond pair, 2 lone pairs. Here also sp3. Tetrahedral. Expected was tetrahedral, but deviated is bent V or angular. Right? So example here is H2O, water. Best example, water. Oh, if the number of electron plates are 4, this is the case. The number of electron plates are 5, AB5 type. AB5. 4 bonding pair, 1 lone pair, total sp3d hybridization, right? Trigonal. If all are bonding, it is trigonal bipyramidal. If all are bonding. If one lone pair enters, it is deviated to what? Called as seesaw structure. Seesaw. Best example, SFO. Okay? Yes, sir. From the same AB5 type. Okay, 3 bonding pair, 2 lone pairs. Same sp3d hybridization, no change. Trigonal bipyramidal. Should be trigonal bipyramidal, but not so. It is a bent T shape. Bent T. An example, Cl chlorine trifluoride. Just I will show you your students. 1, 2, 3, 4. And this is 1. Right? 2, 90, 2 angular, 1. This is seesaw. Jule के चूल्हा रहता है ना ऐसा. Seesaw. If you bend it, it will become like this. This is seesaw. Here I have 3 bonding pair, 2 lone pairs. Almost. You remove this, it will become bent T shape. And this is seesaw. ऐसा अगर आप लिया तो what will become? Seesaw. Right? Okay. That's about, if there are 5 bond pairs, sp3d should be trigonal bipyramidal. This is called seesaw. This is called bent V-shaped structures. Best examples. And lastly, just I will try to wind it up with six bonding pair. Sorry, this is AB4, four bonding, 3 lone pair. I'm extremely sorry, students. AB3 and this is 3 bonding pair, 1 lone pair, and this is 2 bonding pair, 2 lone pairs. Okay, and this is AB4, 4 bonding pair, 1 lone pair. This is 3 bonding pair and 2 lone pair. I'm extremely sorry for that. Just made a correction, right? So, AB3L, 3 bond pair, 2 lone pairs. 2 bond pair, 2 lone pairs. Like this, 4 bond pair, 1 lone pair. 3 bond pair, 2 lone pair. Total will be 5. 5 means sp3. Already I told you in hybrid application, right? Here total 4, sp3 tetrahedral. Here 3, sp2, and here 2, that is sp. And lastly, see, now suppose it is AB4 and 2. 4 bonding pair, 2 lone pairs. Right, and geometry is 4 plus 2, 6 means sp3 into octahedral. Expected geometry, if all are bonding pair, but it is not that it is and made to square plane, that we made to deviated square plane into lone pair, 2 lone pairs, right? Example, best example, xenon tetrafluoride, HCl. Then say AB5L1, 5 bonding pair, 1 lone pair. Got it? Same sp3d2, 5 plus 1, but octahedral. Deviated geometry is square pyramidal. Square pyramidal. Example, HCOF4 or BRL, bromine penta. These are the best examples for 6 pairs of elements. Like this I told you last class. If it is 7 pairs, sp3d3, all bonding pair, it's only one existed example, iodine heptafluoride, pentagonal bipyramidal. There is no any known pair. These are the deviated ones. Please try to remember. 2 pairs, 3 pairs, 4 pairs, 5 and 6. 2 bond pair, 1 lone pair, okay? 3 bond pair, 1 lone pair, 2 bond pair, 2 lone pair, 4 bond pair, 1 lone pair, 3 bond pair, 2 lone pairs, like this. As a lone pair ends at C, there is a disturbance in geometry. If the lone pairs are 0, no deviation in the geometry. Please try to remember this table very perfectly. Very, very important for NEET purpose. Right? Okay. So lastly, students, I want to give you some more last one short trick to find the hybridization of central atom. Hybridization of central atom. To find the hybridization of central atom for NEET purpose, there is a shortcut formula. To find hybridization of central atom. So we have seen the students very importantly formula, shortcut formula, H hybrid orbitals, half V minus V plus number of monovalent groups. Monovalent group means it may be minus charge. Charge on cation plus charge on anion. This is the shortcut form. To find the hybrid orbitals, the number of compound calculation, hybrid orbitals means H, hybrid orbitals. Okay, and geometry, they are fixed. Remember, or hybridization. Geometry or hybrid. Hybridization. degree dilatation. See, number of hydrogens comes to be 2 after calculating this. sp 3, sp 4, sp3, 5, sp3d, right? 6, even it is sp3d2, sp3d2, right? And last is 7, sp3d3. This is the hybridization. This table I have to remember. For sp, we have geometry what? Geometry that is linear, right? For sp2, triangular, planar. For sp3, tetrahedron. For sp3d, trigonal, bipyramidal. And for sp3d2, octahedron. For sp3d3, pentagonal pyramidal. Okay, here bond angle 2 again. Here 0.20. Here 109.28 or 109.5 degrees. Here 120, 90, and here all 90, and here 90 and 70. Right, like this, you have to remember this table. Very, very important for neat purpose. See, this calculation comes to be 2 sp, 3 sp2, 4 sp3, 5 sp3d, 6 sp3d2, 7 sp3d3. These are fixed geometries with the bond angles. Now I will show you some examples using this. How to use this? See, monovalent group, number of monovalent group. It may be monovalent cation or monovalent anion, but not divalent, trivalent or tetravalent. Okay. Coming to lastly, in the examples I will show you now. Some neutral molecule, let us take SO3. What is the hybridization of central atom S? Half. Valence electron of sulfur 6. Whether it is having any monovalent group surrounding it, no. Oxygen is divalent 0. Whether it is any positive charge, no. Negative charge, no. So 6 by 3, that is sp. Over and out. Very simple. First example. Second example, if it is NH4 plus, just observe. Nitrogen atom they ask you. 1 by 2. Valence electron nitrogen 5 plus hydrogen is a monovalent group. How many atoms? 4. Charge minus 1. 0. 9 minus 1. 8 by 2. 4. sp3. Over and out. Third example, if it is CO3 2 minus carbonate radical, carbon. Okay. 1 by 2. Valence electron of the carbon 4. No monovalent group. 1 is 0. Plus 2 charges. So for 6 by 2, 3. sp2. Over and out. And fourth, not only carbonate, you can take even sulfide. SO3 2 minus sulfur. See here. 1 by 2. 6. Plus 0, minus 0, plus 4, 8 by 2. Okay? 8 by 2, 4, that is sp3. What is sulfide radical? Definitely. Okay. And coming to next. See, NH2 minus nitrogen 1 by 2, 5. Monovalent group plus 2, minus 0, plus 1, right? 8 by 2, 4, plus 2. So like this you can calculate central metal atom hybridization by using this concept. Charge on cation you have to deduct it, if it is anion you have to add it. Right? See, like this, see, I have given you ammonium radical, carbonate radical, sulfide radical. This is NH2 minus and SO3. Not only that, even see here, water, H2O. Suppose you are asked to calculate amount of oxygen. Very simple. H2O. See, I will show you. Valence electron 6, monovalent group 2, no charge, no anion. by 2, 4 sp3. 2 bonding pair, 2 lone pair. Right? Like this you can find hybridization of central atom. Not only this, you can take example. Yes, F4. Sulfur tetrachloride, CN. 6 plus 4. Right? That is 10 by 2. 5 sp3b. Definitely you will get this sp3b. Not only sulfur tetrafluoride, students, you can give so many examples. For example, HCF2 xenon dichloride 1 by 2, valence electron 8 plus 2, 10 by 2, 5 sp3b over and out. HCF4 1 by 2, 8 plus 4, 12 by 2, okay, 6 sp3d over and out. HCF6 1, that is 1 by 2, 8 plus 6, 14, 14 by 2, 7 sp3d over and out. Like this. We can easily calculate central atoms hybridization by using this concept. Valence electron plus number of monovalent group minus charge on cation plus charge on atom. That will give you hybridization of the central atom. Even if you don't know the structure, very important super shortcut for finding hybridization. Got it? See, this is how we have completed. Very importantly, once again I have given you the whole table of VSEPR theory, how to calculate hybridization of the central atom, shortcut method for need, compulsory one example. Okay, and then very importantly I told you resonance concept and given you 5 to 6, 7 resonance structure. But for theory purpose, only one ozone is there. So don't worry, practice it. It will help in organic chemistry, and this is more than enough. Thanks from PANCHNATH. Stop here. Enjoy the day. Thank you.